So, I want you to imagine, just for a second, that you are carrying this tray.
Okay.
And it's just absolutely loaded with heavy ceramic mugs, like filled right to the brim with piping hot chocolate.
Oh, man. That's a disaster waiting to happen.
Right. And to make it worse, you are trying to navigate this really rocky, completely uneven hiking trail.
Naturally.
Naturally. But here's the thing. If you lock your arms, keep your spine perfectly rigid and just march forward with completely stiff legs, you're going to spill every single drop of that hot chocolate within like 3 steps.
Oh, 100%. Yeah, you'd wear it all.
Exactly. Because to save the drinks, you instinctively have to use your knees, your wrists, your elbows. You bounce, right? You absorb the shocks. And you kind of isolate the violent motion of your feet hitting the ground from that super delicate tray.
Right. And what you're doing there, without even realizing it, is you are unconsciously calculating the physics of compliance.
The physics of compliance. I like that.
Yeah. I mean, you're letting your body act as this complex suspension system to, negotiate with the terrain rather than just stubbornly fighting it outright.
And that physical negotiation, that exact concept, is what we are dissecting today in this deep dive.
It's a great topic.
It really is. We are going through this massive stack of notes on force storage, damping, and protection, which is basically the invisible, highly engineered mechanical parts that dictate how machines actually survive in a really violent, messy world.
Because machines, just like us carrying that hot chocolate, they need knees and elbows.
They really do.
Yeah.
Because they do not live in a gentle world.
Yeah.
I mean, we might design them in these pristine computer-aided design environments where everything is mathematically perfect.
Right, where there's zero friction and infinite space.
Exactly. But the reality is they hit potholes, they jam up, they overheat, they carry these violently uneven loads, and they just straight up collide with solid objects.
Yeah, and the core premise running through all these sources is that instead of pretending the impact didn't happen or, trying to build a machine strong enough to just ignore it completely.
Which is impossible.
Totally impossible. Instead, these specific parts, the springs, the dampers, the vibration isolators, the shear pins, they're engineered to look at a violent event and say, okay, let's absorb this, let's redirect it, or let's sacrifice a really cheap part before the whole machine is wrecked.
I do want to challenge the baseline assumption here, though, just for a second. Because if we know a machine is going into a high-impact environment, the temptation, and honestly, my first thought when I was reading through this is to just build it out of solid, unbreakable materials.
Old brute force method.
Right, like just make the whole assembly out of a monolithic block of hardened titanium. To me, zero compliance sounds like ultimate strength.
It's a really common intuition, yeah.
But looking through these notes, it struck me that a machine with zero compliance actually operates like someone who never bends emotionally.
Oh, that's an interesting way to put it.
Yeah, like they present this facade of being incredibly tough right up until they take a hit that exceeds their absolute limit. And instead of bruising, they just catastrophically shatter.
That is so accurate. I mean, the actual engineering term for that emotional brittleness is quite literally brittleness.
Really? Just brittleness?
Just brittleness. In metallurgy and structural mechanics, perfect rigidity means you're forcing all the kinetic energy of an impact to find an immediate outlet. The energy of a collision, it doesn't just, vanish just because the material it hits is really hard.
Right, the energy has to go somewhere.
Exactly, it has to be dissipated. If nothing in the machine yields or compresses, that energy concentrates at these microscopic stress risers.
Wait, what's a stress riser?
It's like a tiny physical weak point. So a sharp corner on a gear, a tiny scratch on a steel shaft, or even just the threads of a heavy bolt. The energy focuses there, and it initiates a crack. It breaks gear teeth, it bends drive shafts, it shears off mounting bolts.
Or, I imagine, it transfers that massive shock wave directly into the poor human operator.
Yes, which is the worst-case scenario. So engineering survival isn't about making a machine invincible. It's about fundamentally altering the physics of the violent event itself.
Okay, so we're moving from the concept of just a static, blunt impact to actually managing the physics of time.
Right. We have to look at the force time curve. This is crucial. A stress spike is inherently dangerous because it's concentrating a massive amount of kinetic energy into this infinitesimally small window of time and physical space.
Like a punch instead of a push.
Exactly. The machine doesn't experience a push, it experiences a punch. The mathematical concept here is impulse, which is force multiplied by time.
Force multiplied by time. Okay, so if I want to absorb a specific amount of energy.
You can either do it with a massive amount of force over a single millisecond or a much, much smaller force spread out over, say, a full second.
Right, so a hard impact essentially says huge force, tiny time.
And then a spring or a buffer steps in and intercepts that transmission of energy. It negotiates with that stress. It basically says, let's take that exact same amount of force, but let's spread it over more distance and, crucially, more time.
That makes so much sense.
Yeah, consider a really heavy robotic arm in a car factory, right? If there's a programming error and it swings and slams into a hard steel safety stop.
Oh, man.
Yeah, it might decelerate to zero in, let's say, 1 single millimeter. The peak force generated in that fraction of a millisecond is just astronomical. The arm is probably going to tear itself right off its hinges.
Just sheer destruction.
But if it hits a polyurethane buffer that compresses by, say, 30 millimeters...
then that same kinetic energy is bled off over a way longer duration.
Exactly. The peak force drops by orders of magnitude.
It's landing with bent knees instead of locked legs.
Yeah.
You're literally manipulating time to save your bones. Or, well, the robot's bones.
That's a perfect analogy. And, the sources actually break down this mechanical violence into 4 distinct categories of stress that these parts have to constantly deal with.
Okay, let's go through them. First up is sudden impact.
Right. This is your slamming door, a dropped heavy part, the robotic arm hitting the buffer. It is a singular, violent, linear deceleration.
Boom. Done.
Boom. Second, we have torque.
Which is a twisting force, like a drill bit suddenly jamming in a piece of hardwood while the motor is still spinning at full speed. I've had that almost break my wrist.
It's terrifying when it catches. Or, on a much bigger scale, imagine a massive agricultural tractor.
Okay.
It's pulling a mower, and its power takeoff shaft catches on a hidden rock in the field.
Oh, that sounds expensive.
Very, because the engine has massive rotational inertia, right? It wants to keep spinning. But the rock absolutely refuses to move.
So what happens?
Well, if there's no rotational compliance in that driveline, no give, the twisting force spikes to infinity in milliseconds. The steel drive shaft will simply twist in half like a piece of licorice.
Wow. Like licorice. Just sheared right off.
Yep. So that's torque.
And then the notes dive into the third one. Reciprocation. This is the repeated back and forth motion that seems to be the basis of so much industrial machinery.
It's everywhere.
Engine pistons, high-pressure pump plungers, even the needle bar on a heavy-duty sewing machine.
And reciprocation is incredibly punishing because the component is constantly accelerating to high speeds, stopping completely, and then violently reversing direction.
This is back and forth over and over.
Yeah, every single time that sewing machine needle hits the bottom of its stroke and pulls back up, it creates an inertial shock. The machine has to essentially swallow its own internal violence thousands of times a minute.
Which is wild to think about.
Yeah.
And that actually bleeds right into the fourth category, oscillation and vibration. The notes refer to this as the quiet killer, which, sounds a bit dramatic, but the mechanics behind it are actually terrifying. We think of a washing machine vibrating as just an annoyance, right? Like, oh, it's making noise. But vibration can quietly fatigue solid steel over millions of cycles, even if the individual forces seem completely harmless.
The real danger of vibration lies in resonance. Every physical structure out there has a natural frequency.
Like a tuning fork.
Exactly like a tuning fork. It's the specific rate at which a material wants to vibrate if you strike it. And if an external vibration, say, from a spinning motor, happens to match the natural frequency of the machine's frame,
It amplifies, right?
It amplifies exponentially. The energy compounds upon itself. This is why a poorly balanced washing machine doesn't just make a rattling noise. It can literally walk across the laundry room floor and shake your house to pieces during the spin cycle.
If the internal suspension springs fail to isolate it.
Right, if they fail to isolate that resonant frequency.
And the notes mention this applies on a massive macro scale, too, not just appliances. It's why bridges don't tear themselves apart in high winds.
Ah, aeroelastic flutter?
Yes, aeroelastic flutter, which is a form of oscillation. If engineers didn't install tuned mass dampers and elastomeric bearing pads to interrupt that energy transfer, the bridge would catch that resonant wave and literally shake itself until the steel girders snapped.
It's happened before. So every machine, from a cheap kitchen blender to a massive suspension bridge, is caught in this profound engineering paradox.
Which is?
It must be rigid enough to do useful, precise work. I mean, a construction crane cannot be made of jelly, but it must be forgiving enough to not destroy itself the moment it encounters the chaotic reality of the physical world.
Manage compliance.
Managed compliance, that is the perfect synthesis of the concept.
So having mapped out the violence, the energy, the time, the torque, the resonance,
Mm-hmm.
we needed to reduce the cast of characters, so to speak. The specific mechanical components tasked with actually executing this managed compliance.
Let's meet them.
When I was digesting the sources, I started categorizing them by their job descriptions. Springs, for example, function as a savings account for energy.
That's a great way to look at it.
Right. You deposit kinetic energy into them, they hold it as potential energy, and they eventually have to give it back. Dampers, on the other hand, are the energy eaters. I initially thought of them like a campfire destroying dry wood, just kind of burning up the energy.
But reading deeper into the physics, that's not quite right.
No. A damper is more like trying to sprint waist deep through a swimming pool.
That fluid resistance analogy is highly accurate for dampers. The harder and faster you try to push against the water, the more aggressively the water pushes back. It's a velocity-dependent resistance.
Right.
But let's look at your energy bankers first. The springs. They operate entirely on the principle of elastic potential energy. They deform under mechanical stress, store that work within their atomic structure, and then return to their original shape when the load is removed.
And we always default to picturing coil springs, right, like a slinky.
Mm-hmm.
But the sources highlight that springs negotiate force across every axis.
Absolutely. You have compression springs that get shorter, like the springs under a mattress or a car's strut.
You have extension springs that get longer and pull back, like the massive coiled springs on a garage door or a trampoline.
You also have torsion springs that absorb twisting force. Think of the mechanism inside a mousetrap or a heavy-duty clipboard.
Oh, right.
And bending springs that flex along their length, like a fiberglass archery bow or the stacked steel leaf springs on the rear axle of a heavy pickup truck.
Now, the physics underlying the spring is where my mind was completely blown. The text references Hooke's law.
Hooke's law,
Which, at its most basic, says force equals stiffness times displacement. Meaning, if you push twice as hard, the spring compresses twice as far. It's a very simple linear relationship.
Correct.
But the actual energy stored in that spring, that is not linear at all.
Not even a little bit. The stored energy is quadratic.
Quadratic. Explain that for us.
The equation is that energy equals 1/2 of the stiffness multiplied by the displacement squared. Squared. To translate that out of the textbook and into reality, if you compress a heavy coil spring by 1 inch, it takes a certain amount of energy. If you compress it by 2 inches, you haven't just doubled the energy stored.
You've stored 4 times the destructive power.
Exactly. 4 times the energy.
Which makes springs incredibly powerful accumulators of force.
Mm-hmm.
But also wildly dangerous if that energy is released unpredictably, right? Like if a fully tensioned garage door spring snaps.
It releases all of that squared potential energy instantly. It can be lethal.
Yeah, it's terrifying. And this quadratic energy curve is why a spring alone is actually a massive engineering problem.
Oh, definitely. Think about hitting a deep pothole in a car that only had springs for a suspension.
Okay, no dampers, just springs.
Right. The spring would compress beautifully, absorbing the impact and protecting the chassis. But a spring is a savings account. It must return the deposit.
So it bounces back.
It violently releases that stored energy, pushing the car upward. Then gravity pulls it back down, compressing the spring again. Your car would bounce up and down essentially forever, or at least until the minute internal friction of the steel slowly bled the energy away.
And that is exactly where the energy eaters enter the chat. You cannot have a spring without a damper if you want any kind of stability.
You really can't. Dampers bleed off that stored kinetic motion and permanently convert it into thermal energy, or heat.
Heat. It just turns the bounce into heat.
Exactly. The most common industrial and automotive dampers use viscous flow. You have a piston moving inside a sealed cylinder completely filled with hydraulic oil. As the suspension moves, it forces that oil through microscopic orifices and spring-loaded shims built into the piston.
So this goes back to the swimming pool analogy.
Precisely. Fluid dynamics dictate that the faster you try to force a liquid through a tiny hole, the resistance doesn't just increase linearly, it increases exponentially. So if you slowly push down on the bumper of your car, the oil flows easily through the piston valves. The car dips smoothly. But if you hit a speed bump at 60 miles an hour...
the piston tries to move through that oil violently.
Yes. The fluid resists, creating immense hydraulic pressure, which turns the kinetic energy of the bump directly into heat within the oil.
So the spring handles the sheer force of the bump, but the damper handles the chaotic aftermath.
Exactly.
And this clears up a massive point of confusion I've always had. And honestly, I guarantee a lot of you listening have had this too. When we talk about shock absorbers on a vehicle, the name is actually a lie.
It is a total misnomer.
They do not absorb the shock or hold the weight of the car. The steel spring holds the weight. The shock absorber is purely a damper designed to stop the spring from bouncing uncontrollably.
That's right. All shock absorbers are dampers, but not all dampers are shock absorbers.
Right, like the tiny hydraulic cylinder that allows a high-end kitchen drawer to soft close without slamming.
That's a damper. It's dissipating the kinetic energy of the drawer into heat. You wouldn't call it a shock absorber, but it operates on the exact same physics as the suspension on a massive freight train.
It's so cool when you connect those dots. Okay, so then we have what I call the peacekeepers, the vibration isolators and the buffers.
Right, the third category.
And these aren't dealing with massive singular impacts or huge suspension travel, but rather the constant grinding reality of resonance we talked about earlier.
Yes, these are your heavy elastomeric machine mounts, your dense cork equipment pads, your pneumatic air bladders. They utilize mass, stiffness, and their own natural frequency to create an acoustic and physical boundary that stops vibration from spreading.
The notes gave the example of a high-end microphone shock mount in a recording studio.
A perfect example. It uses a web of elastic bands to suspend the microphone. It is tuned so that the low-frequency thumping of someone, say, tapping a desk.
It simply cannot cross the elastic boundary to reach the microphone element.
Exactly. It's an energy border.
Or like the heavy rubber feet on a high-speed blender that prevent the massive vibration of crushing ice from transmitting to your kitchen counter and literally shaking your glasses out of the cupboards.
Right. Buffers operate in a similar peacekeeping space, but they are specifically the do not cross this line components.
Like the dense rubber stopper at the end of a heavy sliding barn door track?
Yes. It sits quietly until someone throws the door open too hard, at which point it absorbs the impact to keep the door from flying off the rails.
But out of all these components we're talking about, here's where the engineering philosophy gets truly, truly fascinating.
Ah, the martyrs.
The martyrs.
Yeah.
The overload clutches, the shear pins, the mechanical fuse links, because everything we have discussed so far, springs, dampers, isolators, is meant to survive the force.
Right.
They absorb and they recover.
They're resilient.
Right. But these specific parts are engineered for deliberate, catastrophic failure.
It is the philosophy of the mechanical fuse, which is perhaps the most elegant solution to unpredictable overload.
I love this concept. Walk us through it.
So, in a rotating mechanical system, like a massive agricultural conveyor belt or an industrial snowblower auger, if a large rock jams the mechanism, the engine or the motor is going to aggressively keep trying to turn.
It doesn't know there's a rock.
Exactly. That twisting force, the torque, will spike to destructive levels instantly. Now, if the entire driveline is built to be perfectly strong and rigid, that energy will find the weakest link.
Right, the energy has to go somewhere.
And usually that means the electric motor will pull too much current and melt its windings, or the main transmission gearbox will just shatter.
Which is a catastrophic failure.
You are looking at a failure that costs thousands of dollars and requires days of specialized labor to fix.
But if you design the system with a shear pin,
you introduce a localized, intentional weak point. A shear pin is typically a small, cheap, maybe $5 piece of brass, or a very specific, highly calibrated grade of soft steel. It connects the driving shaft to the driven component.
and it's strong enough for normal use, right?
Exactly. It's engineered to transmit normal operating torque all day long, but it is mathematically designed to cleanly snap in half the moment the torque limit exceeds a safe threshold.
So the rock jams the auger, the torque spikes, the pin snaps instantly.
Boom.
Boom. Suddenly the engine is spinning completely freely, safely disconnected from the jammed auger. The expensive gearbox is perfectly safe.
It's a beautiful thing.
You just shut the machine down, pull the rock out of the blades, slide a new $5 pin into the shaft, and you are back to work in 5 minutes.
It is the ultimate sacrificial protection. It is a calculated judgment by the engineer that it is vastly better to lose a small, cheap, easily accessible component than to risk the expensive, highly complex core of the machine.
Overload clutches accomplish the same goal, right?
Yes, but instead of physically breaking a pin, they use friction discs or spring-loaded detents that slip or disengage under extreme torque. They chatter or spin freely until the jam is cleared, and then they can reset without requiring a replacement part.
Is Brilliant, pragmatic engineering. But reading this immediately brought up a massive practical question for anyone who has ever tried to maintain their own equipment.
I think I know where you're going with this.
Let's go back to the snowblower example. You hit a chunk of solid ice hidden under the snow. The auger jams and the shear pin snaps perfectly, doing exactly what it was designed to do.
Like a successful failure.
Right. So you trudge back to your cold garage workbench, open your drawer, and realize you don't have the exact manufacturer replacement pin.
Happens all the time.
But you do have a heavy-duty hardened steel bolt from the hardware store that is the exact same diameter. It slides perfectly into the hole. Why shouldn't you just use that hardened bolt to finish clearing the driveway?
Because by swapping that material, you are fundamentally corrupting the secret language of materials that the engineers designed.
That's a great phrase, the secret language of materials.
Replacing a calibrated soft metal shear pin with a hardened steel hardware bolt is exactly the same logic as taking a blown electrical fuse out of your home's breaker box and jamming a solid iron nail in its place.
Oh, wow. Yeah, it works beautifully to bridge the gap.
Right up until it burns your entire house down.
Exactly.
It's precisely the same outcome mechanically. If you put a hardened grade 8 bolt in that snowblower's auger shaft, the next time it hits a chunk of ice, that bolt will absolutely not shear. It is too strong. It refuses to be the martyr.
So that massive torque spike travels right past the bolt?
It travels right past the bolt, hunting down the driveline for the next weakest link. That will almost certainly be the delicate internal brass gears of the auger transmission.
Because you wanted to save a trip to the hardware store, you just traded a $3 inconvenience for a $300 catastrophic mechanical failure.
Exactly, which highlights a vital lesson from these sources. Knowing what shape or size part you need isn't nearly enough. The actual physics of how a component handles stress is entirely dictated by what it is made of down to the molecular level.
Material science. It's the invisible foundation supporting this entire field of managed compliance.
It really is. We can look at steel as the prime example here. Steel is a fantastic material for springs because it possesses a very high elastic limit and incredible fatigue resistance. But you can't just coil any old steel wire and call it a spring.
Right, the notes talk about the treatment process.
To create a high-quality component, the steel must undergo rigorous heat treatment. It must be heated to a specific temperature to alter its crystalline structure, then quenched rapidly in oil or water to freeze that hard structure in place.
And finally tempered, right?
Tempered, yes. Reheated slowly to draw out the brittleness and dial in the exact ratio of hardness to toughness.
Now, I was fascinated by the surface-level violence we inflict on steel just to make it survive. The sources detail a manufacturing process called shot peening.
Shot peening is wild.
It sounds like a medieval torture method for metal. You are basically bombarding the steel with tiny metal balls. Why would we intentionally batter the surface of a perfectly good spring?
It seems so counterintuitive, but it solves a deep physical problem. When a coil spring compresses, the steel wire itself is actually twisting. The outer surface of the wire is put under extreme tension. The atoms are literally being pulled apart.
Okay, tension.
And as we established earlier, microscopic fatigue cracks almost always start at the surface of a material when it is under tension.
Right, the stress risers.
So shot peening fires millions of tiny, hard spherical balls at the spring at extremely high velocity. Each tiny impact creates a microscopic dimple, which forcibly stretches the surface layer.
So you are packing the surface molecules tighter together.
Yes. You are preloading the surface of the metal with a layer of permanent compressive stress. The molecules are squeezed tightly together. So when the spring is actually installed and put under tension, that applied tension first has to overcome the built-in compression before the surface ever actually experiences a tearing force.
That is genius.
Isn't it? Pre-stressing the metal in compression dramatically extends the life of a spring that is expected to bounce millions of times on a vehicle.
That is incredible foresight in manufacturing. And the tolerances required for these parts are just staggering. The notes dive into the piston rod inside a high-pressure hydraulic shock absorber.
Oh, the surface finish on those rods.
Right. This rod has to slide in and out of the oil-filled cylinder thousands of times an hour. If there is a tiny, almost microscopic surface flaw on that hardened steel rod, or if the factory grinding process left a chatter mark even a fraction of a millimeter deep,
that microscopic flaw becomes a weapon. Truly. Every time that rod slides rapidly past the tight rubber hydraulic seals meant to keep the pressurized oil inside, that tiny scratch acts like a jagged file.
just tearing at the rubber.
It will systematically shred the lip of the rubber seal. Within a few thousand miles, the seal is destroyed, the hydraulic fluid leaks out, and the damper is dead. It becomes nothing more than a hollow tube.
Which brings us perfectly to the magic of rubber. Because we've talked about steel, but rubber is uniquely suited for this category of protection because it essentially performs two jobs simultaneously.
It's a miracle material.
It really is. It stores energy elastically like a seal spring, but it also has high internal friction, meaning it dissipates energy as heat like a fluid damper.
The engineering term for that dual property is hysteresis.
Hysteresis.
Yeah. When rubber deforms under a load, the polymer chains slide against each other, creating internal friction. When the load is removed, the rubber doesn't snap back with 100% of the energy it absorbed. A significant portion of that energy was lost as heat.
This makes elastomeric materials invaluable for engine mounts and vibration isolators.
Absolutely invaluable.
But the notes make a huge point that we can't just treat all rubber as the same material.
Yeah.
I mean, I always operated under the assumption that rubber is rubber. A tire, a shoe sole, an engine. I figured it was all the same basic stuff.
Most people do. But the specific chemical compound changes everything based on the operating environment.
Give us an example.
Take natural rubber, harvested from trees. It actually possesses fantastic elasticity and incredible vibration damping properties. But its chemical structure makes it highly vulnerable.
Vulnerable to what?
Well, if you mold a natural rubber mount and place it deep inside an engine bay where it is exposed to high heat, dripping motor oil, and fuel vapors,
It degrades.
it will quickly swell up, turn into a spongy mess, and just disintegrate.
Wow, so nature provides the blueprint, but chemistry has to adapt it for survival.
Exactly why engineers rely on synthetic elastomers. For an engine mount exposed to petrochemicals, they formulate nitrile rubber, which heavily resists oil degradation.
Okay, nitrile for oil.
But what if the part is outdoors, constantly baked by the sun? Natural rubber and nitrile both crack rapidly under ultraviolet light. So chemists developed EPDM,
EPDM.
ethylene propylene diane monomer.
Say that 3 times fast.
Huh? Right. It is a synthetic rubber with a fully saturated polymer backbone. Without getting lost in organic chemistry, that saturated backbone means that ozone and UV light simply have nowhere to attack the molecular bonds.
So it lasts longer outside.
EPDM can sit on a hot roof as a vibration pad for an air conditioning unit for 20 years without cracking.
That's amazing. But rubber still has a dark side, right? Even the highly engineered synthetics. The sources highlight something called creep. It sounds sinister, and mechanically it kind of is.
Creep is the enemy of long-term isolation.
Yeah, rubber ages, and if it is subjected to a heavy, constant load over years, like holding up a heavy engine block, it slowly, permanently deforms.
It just sags.
An engine mount might just slowly sag, millimeter by millimeter, over a decade, until the engine is resting solidly against the metal frame, entirely bypassing the rubber. Suddenly, all that engine vibration is transmitted directly into the cabin of the car.
It's a very common failure mode. But moving beyond traditional steel and rubber, the sources showcase how advanced exotic materials are radically shifting the landscape of managed compliance. We are seeing technologies that border on science fiction.
Oh, this part was wild. The magnetorheological fluid.
Yes, being deployed in high-end automotive suspension systems and even seismic dampers for architecture.
I literally read that section 3 times. Magnetorheological fluid. Break down how that actually works, because it honestly sounds like magic.
It's brilliant applied physics. So the damper is filled with a synthetic fluid that is heavily saturated with microscopic, magnetically soft iron nanoparticles.
Iron nanoparticles floating in oil.
Right. In its resting state, the iron particles float randomly and the liquid flows easily through the damper valves, much like standard hydraulic oil. It provides a soft, comfortable ride.
But then a computer gets involved.
The damper piston contains an electromagnetic coil. Sensors on the car read the road surface hundreds of times a second. If the computer detects a massive pothole,
It fires an electrical current into that coil in milliseconds.
exactly. And the magnetic field instantly forces all those random iron nanoparticles to align into rigid, microscopic fibrous structures along the magnetic flux lines. The fluid instantaneously thickens into a semi-solid paste.
That is just, wow.
The damper becomes incredibly stiff, absorbs the violent impact of the pothole, and then the computer cuts the power, returning the fluid to a liquid state before the wheel even hits the next bump. It is a damper that adapts its physical properties in real time.
That is mind-bending. The machine actively negotiating with the terrain instantly.
Yeah.
But, the notes also bring up advanced materials that present massive societal challenges, like carbon fiber.
Yeah, that's the flip side.
We see composite leaf springs entering the market. They are incredibly strong and a fraction of the weight of steel, which is obviously fantastic for fuel efficiency. But there is a massive catch.
The catch is the end of the product's life cycle: recycling. We discussed earlier that steel is fundamentally infinitely recyclable. Its inherent magnetic properties make it incredibly easy to separate from massive municipal waste streams. You melt it down, and you make a new spring.
But carbon fiber is a composite material. It consists of woven carbon threads permanently embedded in a hardened thermoset plastic resin.
Right, and you can't just melt a thermoset plastic, it burns.
It just burns.
Correct. It is notoriously difficult, chemically complex, and highly energy-intensive to separate the fibers from the resin to reclaim the material. When a carbon fiber composite spring fails or the vehicle is scrapped, it is vastly more likely to end up sitting in a landfill for centuries than a traditional steel leaf spring.
Which bleeds perfectly into the manufacturing realities highlighted in the text. Like, why did these parts fail prematurely, especially the cheaper aftermarket ones? The sources emphasize that it's rarely a spectacular design flaw. It is usually invisible, systemic compromises in manufacturing.
The hidden flaws are always the most dangerous. Consider a heavy cast iron housing for a vibration isolator. To save money, a factory might speed up the casting process, leading to porosity.
Porosity meaning tiny, microscopic air bubbles trapped inside the solid metal during the cooling process.
Yes. On the outside, the metal bracket looks perfectly solid and heavy, you'd never know. But internally, it resembles Swiss cheese.
Oh, man.
Under the repeated stress of an impact, those internal air bubbles act as massive stress risers, and the heavy iron bracket simply snaps in half without warning.
Or consider the chemical bonding process. A heavy-duty engine mount is basically a piece of thick rubber sandwiched between two steel plates. But the rubber isn't just glued to the steel, right?
No, it requires a complex, heat-activated chemical bonding agent applied perfectly in the mold. If a cheap factory cuts corners on cleaning the steel or regulating the mold temperature, the chemical bond is weak.
So under extreme torque.
The rubber simply rips cleanly away from the steel plate, rendering the mount entirely useless.
The most terrifying example in the notes was counterfeit shock absorbers. The global aftermarket is just flooded with them. They might look completely identical to a premium brand on the outside, the exact same paint color, meticulously copied warning stickers, same heavy box.
But internally, the precision is entirely absent. Inside a counterfeit damper, the complex spring-loaded valving system that dictates the fluid flow might be replaced by cheap, stamped washers that just bend under pressure.
Which ruins the damping.
Totally. And instead of high-temperature synthetic hydraulic oil, they might use cheap mineral oil that foams up and boils when the shock gets hot on a rough road.
Wait, foams up?
Yeah, and once the oil foams, it is full of air bubbles. Air compresses, fluid does not, so the damper loses all resistance.
And the internal rubber seals might be made of inferior compounds that wear away against the unpolished piston rod within a month.
And this is the real issue. In a passenger vehicle operating at highway speeds, a failed shock absorber isn't just a bouncy nuisance. It drastically increases stopping distance and makes the car uncontrollable in an emergency swerve. It is a critical safety hazard masquerading as a bargain.
This opens up a huge conversation about what this all means for the end user. For the person listening right now who is just trying to fix an unbalanced washing machine or replace a torn transmission mount on their commuter car, we are talking about an entire category of parts that are explicitly designed to wear out, take physical abuse, or intentionally sacrifice themselves.
And the physical reality of how these parts handle force creates an inescapable economic reality for our entire society.
It really does.
It forces a profound confrontation with the concepts of ownership, the right to repair movement, and the sheer environmental footprint of the global supply chain we rely on.
I feel like everyone has a deeply frustrating story about a household appliance breaking because one tiny plastic damper failed, or one sacrificial gear sheared. You call the manufacturer to order a replacement, and they cheerfully tell you, oh, we don't sell that $3 part individually. You have to buy the entire $300 drum assembly.
Or worse, the service tech tells you it's cheaper to just throw the whole machine out and buy a new one.
Exactly. It's madness.
It's a profound tension between engineering efficiency and economic waste. Let's look at how these replacement parts are even identified, what the sources call the ID crisis. You are dealing with Model numbers, part numbers, serial numbers, and manufacturing lot numbers.
It's a nightmare to navigate.
A model number might tell you the general family of a machine, but the part number specifies the precise physics.
I saw a great example of this in the notes regarding rubber hardness, the Shore A scale. For those not familiar, the Shore A scale measures the hardness of flexible materials. A gummy bear might be a 10 on the Shore, a scale incredibly soft. A standard rubber band is maybe a 20. A car tire tread is around a 60, and a hard skateboard wheel pushes up into the 90s.
Wait. So imagine a technician ordering a vibration isolation mount for a massive industrial pump. They might have two mounts on the table that look completely identical to the naked eye. The steel threads are the same, the diameter is the same, the rubber looks black and identical. But the part numbers differ by 1 digit.
Just 1 digit.
One is made of natural rubber with a soft shore, a hardness of 40. The other is made of nitrile rubber with a stiff shore, a hardness of 70.
So if the technician assumes they are interchangeable and puts the soft 40 hardness mount under that heavy high-torque pump,
the sheer weight will just crush the rubber flat instantly. The mount will tear in half the first time the pump turns on.
but if they put the stiff 70 hardness mount under a delicate piece of medical lab equipment that needed soft isolation,
The mount will be far too rigid and will transmit every single vibration from the floor right into the sensitive lasers of the equipment.
identical form, fundamentally different function.
And this granular complexity drives the entire repair versus replace debate that plagues modern manufacturing. On one end of the spectrum, you have highly durable, endlessly rebuildable designs.
Like what?
Think of a high-end racing shock absorber on an off-road truck. It is designed to be completely dismantled. You can unthread the cap, drain the spent oil, replace the worn Teflon seals, change the thickness of the internal shims to tune the damping curve, refill it with fresh oil, and keep that same heavy aluminum housing running flawlessly for decades.
Or industrial overload clutches in a factory, where instead of replacing a massive steel assembly, a maintenance worker just swaps out the worn friction brake discs every few years.
Exactly. But the reality of consumer goods is trapped on the total opposite end of that spectrum. We are dominated by disposable designs.
Which is so frustrating.
Take the friction damper on a modern consumer washing machine. It is permanently sealed at the factory. It's incredibly cheap to manufacture by the millions. It guarantees consistent performance right off the assembly line. And it is very easy for the brand to control warranty claims because the entire unit is swapped out at once.
But when the internal seal on that damper eventually wears out from the friction,
You can't open it to replace a 10-cent rubber O-ring. The entire unit becomes plastic and metal garbage.
and often it is a mixed material piece of garbage that is impossible to recycle economically.
Right. A sealed automotive strut, for instance, contains a heavy steel tube, an aluminum bracket, toxic hydraulic oil, synthetic rubber seals, and Teflon guide rings, all permanently crimped together.
When it fails, separating those vastly different materials is so labor-intensive that it just isn't economically viable. Millions of these heavy metal assemblies simply end up buried in landfills every year.
It creates a really challenging environmental trade-off. We willingly throw away a sacrificial part in order to save a larger machine. Throwing away a broken brass shear pin to save a tractor's transmission is an obvious ethical and environmental win.
Sure.
But discarding a massive multi-material sealed suspension strut simply because a $2 internal shaft seal developed a leak, that feels like a profound environmental loss.
And this reliance on highly specific replacement parts creates incredible fragility in the global supply chain. The notes detail the vast geography of raw materials required just to make these basic components. We need bauxite mined in Australia to refine into the aluminum for shock bodies. We rely on petrochemicals refined in Texas to synthesize the EPDM rubber for isolators. We need specialized steel alloys forged in Germany for high-stress coil springs.
All of these materials crisscross the globe on container ships. A factory line producing million-dollar electrical transformers can be brought to a dead halt because a shipping container holding a specific $3 rubber vibration mount is delayed at a port.
And there is no known safe chemical equivalent available locally.
Which is exactly why the right to repair movement is so vital, particularly for this specific category of force-managing components. Farmers in the field, independent mechanics in small towns, and industrial maintenance crews absolutely need access to the technical documentation.
They need to know the exact shore hardness, the exact torque specification, the precise damping curve of a part.
So they can source safe aftermarket replacements or creatively rebuild the components themselves when the global supply chain falters.
I read a detail in the sources about modern farm equipment that blew my mind. Some manufacturers are now using DRM digital rights management software on physical wear parts.
It is a highly controversial practice. The manufacturer places a microchip inside a component, like an active suspension damper or an electronic clutch. When the part fails, you cannot just bolt on a structurally identical replacement from a third-party supplier.
Because the main computer of the tractor demands a proprietary software handshake from the microchip in the new part. If the part doesn't have the authorized digital signature, the tractor simply refuses to operate, even though the physical mechanics of the new part are flawless.
The manufacturer has effectively monopolized the repair of a basic physical wear item by locking it behind digital cryptography. A farmer might have the tools, the skills, and the physical replacement part to fix their own suspension in the middle of a harvest, but they are paralyzed by a software lock out of their control.
It is wild to think that something as brutally physical, as autonomous as a shock absorber taking a hit from a rock, is getting entangled in digital copyright law.
It really is.
But zooming out from the factory floor, from the repair shops and the supply chain bottlenecks, the sources make this beautiful, overarching philosophical point. These humble hidden parts, the coiled springs, the oil-filled dampers, the rubber isolators, they are actually the fundamental building blocks that allowed human civilization to scale up to the modern era.
It is not an overstatement to say that without the development of managed compliance, the Industrial Revolution would have literally shaken itself to pieces. Steam engines would have vibrated apart, early internal combustion engines would have shattered their own mounts, and precision manufacturing would have been impossible.
There is this recurring, almost poetic theme woven through the source notes that refers to a concept labeled ADDI.
ADDI.
The notes use ADDI as an avatar to represent resilience, nature, grief, fire, motion, and learning to bounce back from intense hardship. It explicitly compares mechanical compliance to human emotional regulation, and the metaphor maps perfectly.
It does.
We all need springs in our psychological makeup, the elastic ability to hold on to hope, to absorb a blow without breaking, and to recover our energy. When you get dampers, the emotional capacity to take a deep breath, reflect, and bleed off the intense heat of a chaotic situation so we don't bounce out of control and overreact.
Right.
And we absolutely need sheer, pins-firm boundaries and the willingness to make small, deliberate sacrifices or to step away from a toxic situation to prevent a total mental burnout.
It is a striking and deeply accurate metaphor because engineering does not attempt to defeat nature. It is a prolonged negotiation with nature's rules. When we design these parts, we are fundamentally mimicking the brilliance of biology.
Nature did it first.
A tree branch doesn't try to stand rigidly against a hurricane. It acts as a bending spring, bowing to the wind to survive. The cartilage cushioning a human knee joint is a highly evolved polymer buffer, absorbing shock and distributing loads while secreting its own synovial fluid as a viscous damper. Tendons store elastic energy with every step we take.
We imitate the resilience of nature in order to survive the violence of nature.
And this imitation scales up to our most massive societal achievements. We wouldn't have modern mass cities without this understanding of force. A skyscraper like Taipei 101 isn't a rigid block of concrete defying the weather. It is designed to sway several feet in typhoon winds.
And to prevent the swaying from becoming destructive,
engineers suspended a massive 660 metric ton steel pendulum near the top of the building.
a tuned mass damper.
Yes. It is suspended on thick steel cables and connected to massive hydraulic shock absorbers. When the wind pushes the building to the right, the massive pendulum's inertia makes it swing to the left. The hydraulic dampers bleed off the kinetic energy of the building's sway, turning the force of a typhoon into heat in the hydraulic oil.
Without that managed compliance, the building would snap. High-speed rail networks rely on astonishingly complex active suspension systems to keep a train perfectly level and on the tracks at 200 miles an hour. Precision medical imaging, like MRI machines, requires profound vibration isolation.
If the tiny, imperceptible vibrations from a hospital's HVAC system weren't damped out by elastomeric mounts, the microscopic resolution of the brain scan would be an unreadable blur.
It all comes down to the hidden labor of maintenance. Modern civilization relies utterly on maintenance technicians, mechanics, and engineers whose work remains entirely invisible to the public until something breaks. A high-quality shock absorber does not announce its presence. It quietly makes the road feel smooth. A perfectly calibrated buffer prevents the loud bang of a collision. We only ever notice these parts when they fail. But the engineering and maintenance required to prevent that failure is a profound structural form of care for society.
We depend fundamentally on small, sacrificial things, and we depend even more heavily on the people who understand how those small things negotiate with force.
So, synthesizing everything we've explored from this massive stack of research, we've seen how machines handle the violent, chaotic reality of the physical world. They do not survive by being perfectly rigid and stubbornly fighting the force. They survive by bending, by absorbing the kinetic energy, by delaying the transfer of shock over time, and sometimes by breaking a small piece on purpose to save the whole. They negotiate with stress.
They serve as the mechanical coping mechanisms of our modern industrial world.
Which leaves me with one final, deeply provocative thought pulled from the very end of the source text. As we move deeper into the digital era, the notes mention research facilities developing entirely new paradigms. Regenerative shock absorbers that harvest the energy of a bumpy road to charge a battery, and active suspension systems entirely controlled by predictive software algorithms.
That's the new frontier.
But as our machines transition from relying on passive, purely physical parts, like the simple elegance of a coiled steel spring or a dependable brass shear pin, to relying on active, sensor-controlled, heavily software-reliant damping systems. What happens when a machine's physical resilience requires a software update instead of a mechanic's wrench?
That is the big question.
Do we lose that honest, unhackable physical truth of stress negotiation when we hide it all behind a microchip and proprietary code? If the digital system crashes or the software handshake fails, does the rigid world finally shatter the machine? It is definitely something to mull over the next time you hit a deep pothole and your car simply bounces back.
A fascinating dilemma for the future of resilient engineering.
Thanks for diving into the mechanics of survival with us. See you next time.